suppose we have a population random variable x, which is uniformly distributed between -3 and 5. Now it's relatively straightforward to show that the expectation of this random variable is 1 and the variance is 16/3. But suppose that we didn't know what the expectation of the random variable was and we wanted to estimate it. One way that we might do this is by taking a sample from the population and calculating the sample mean as an estimator of the population average. So let's suppose that we take 300 observations from this population and we denote those observations x1, x2, x3 all the way up to x300. And we use these 300 observations to construct the sample mean x bar, which is going to be equal to 1/300 times by the sum of all of our observations. So we're going to add up all of our observations and divide by 300. Now the first question we might want to think about is, do we know anything for certain about the sample mean? Well, the only thing that we can say with any real certainty is that the sample mean will be somewhere between -3 and 5. We know that all of the observations of x are drawn from a uniform distribution between -3 and 5, so it must also be the case that the sample mean is somewhere between -3 and 5. Now, because we've got a relatively large number of observations, we've got 300 observations here, it's most likely that the sample mean will be somewhere close to the population average, but we don't know with any certainty what value x bar will have. Now we've previously seen that if the observations are independent and identically distributed, the sample mean is an unbiased estimator of the population average. That is, the expectation of x bar is equal to the expectation of x, which in this case would be equal to 1. Furthermore, we've seen that if the observations are IID, then the variance of the sample mean is equal to the variance of the population random variable divided by the number of observations, which would be equal to the variance of x here divided by 300, because we've got 300 observations, which is going to be equal to 16/3 divided by 300, which is going to be equal to 16/900. The final thing that we can say about the sample mean is that provided the sample size is large enough, and by large enough here we mean that the sample size is more than about 30 to 50 observations. Here we've got 300 observations, then by the central limit theorem we can write that the sample mean will be approximately normally distributed with expectation equal to the expectation of x, so that will be equal to 1, and variance equal to the variance of x divided by the number of observations, so that's 16/900. So we know that the sample mean will be approximately normally distributed with expectation 1 and variance 16/900, but suppose that we wanted to calculate the probability of randomly observing a sample mean less than or equal to, let's say, 0.8. How would we go about doing this? Well, the first thing we can do is we can think about this diagrammatically. We can think about the probability of observing a sample mean less than or equal to 0.8 as being the area under the probability density function of the sample mean to the left of 0.8. So this shaded area will be the probability that x bar is less than or equal to 0.8. Now if we want to find the shaded area, or the probability that x bar is less than or equal to 0.8, one thing that we could do is we could standardize the distribution. Remember, if we've got a normally distributed variable, like the sample mean here, we can standardize it to a z statistic by subtracting the expected value of our variable and dividing through by the square root of the variance of that normally distributed variable. And this resulting distribution will follow a normal distribution with expectation 0 and variance 1. So we effectively want to find the value of z, or little z we could say, such that the probability that a randomly drawn observation from the standard normal distribution is less than or equal to little z is the same as the probability that x bar is less than or equal to 0.8. So we're going to try and find what value this little z would take would be equivalent to x bar being less than or equal to 0.8. So we're going to construct our value of little z, which is going to be equal to our value that we're interested in from x bar, so that's 0.8, minus the expected value of x bar. We know that the expected value of x bar is going to be equal to 1, and divide through by the square root of the variance of x bar, which is the same as the square root of 16 over 900. And this is the same as minus 0.2 divided by 4 over 30, which is the same as minus 1.5. So what that means is that the probability that x bar is less than or equal to 0.8 is the same as the probability of randomly sampling an observation from the standard normal being less than or equal to minus 1.5. So we could try and look up this probability from the normal distribution tables. We could try and find capital phi of minus 1.5, which remember is the same as the probability that z is less than or equal to minus 1.5. But the problem is that the normal distribution tables are only defined for positive values of z. So what we could do is we could use the fact that the standard normal distribution is symmetric around 0. So the probability that z is less than or equal to minus 1.5 is the same as the probability that z is greater than or equal to plus 1.5. Now again, we can't directly observe this from the tables, but we know that the probability that z is greater than or equal to 1.5 is going to be the same as 1 minus the probability that z is less than or equal to 1.5, because the total area under the curve must be equal to 1, and this probability is just given as phi of 1.5 in the table. So we're going to look for 1 minus phi of 1.5. So I've got an extract from the normal distribution tables here, and what we would need to do is we need to look for a z equal to 1.5, and this would give us the probability of randomly observing a observation of z which is less than or equal to 1.5, which would give us a probability equal to phi of 1.5 is equal to 0.9332. But remember, this is not what we want. What we want is the probability that z is greater than or equal to 1.5, which is going to be equal to 1 minus phi of 1.5, which is equal to 1 minus 0.9332, which is equal to 0.0668. That's the probability that z is greater than or equal to 1.5, but it's also, by symmetry, the probability that z is less than or equal to minus 1.5. So from this we can see that the probability of randomly observing a z less than or equal to minus 1.5 is 0.0668, and because we've standardized a normal distribution, that means that also our original sample mean, the probability that x bar is less than or equal to 0.8, is also going to be equal to 0.0668.